So unfortunately, I did not record the lecture number 3 today, so I'm doing it now and will be posting it online. So this is lecture 3, April 5th, 2021. What we discussed last time was how to represent any system as a single degree of freedom system, knowing that any structure in the world has 3 properties: mass, stiffness, and damping. And if we can identify those and consider that the entire motion of that structure can be represented by measuring the displacement at a single location or single degree of freedom system, we can represent that structure as a single degree of freedom system. We also said that in fact, main objectives of mechanical vibrations are to do that modeling or identify the single degree of freedom system for any structure and then find a response. So we will focus for now on solving the differential equation for a single degree of freedom system for a special case, and then using that to show you how to set up or a single degree of freedom system model for any mechanical vibration. So this was the model in general that we described as single degree of freedom system. And then we set up the equation of motion. But we also, as I mentioned last time, there are basically 4 categories that we are going to study. And the first case is the free vibration of an undamped system. So that means in this model, we do not have this element and we have no forcing acting on the system. The forcing function has applied on the system. Now it has disappeared, so the system is vibrating on its own. Why is it that this study of this free, undamped vibratory system is important? First of all, this model is really a first step for solving in general the mechanical vibration analysis of single degree of freedom systems. Also, it helps us to solve the equation of motion in its most basic form. And as we will see, this solution shows us the first building block that introduces fundamental quantities in any dynamic system, such as natural frequency and so on. And also, it is a first building block for multi-degree of freedom systems analysis. So let's begin. This is the general equation of motion for a single degree of freedom system, as we described. So if the damping or the energy dissipation doesn't exist and system is vibrating on its own, this would become the equation of motion. One may say, okay, what does it mean that system vibrates on its own? As I said, you have an initial disturbance that has disappeared, but system continues to vibrate. So we want to show you how to solve this equation. And we just simply use the basic classic approach for solving differential equations. This is a second order linear homogeneous equation. How do you solve that? First, I would divide both sides by m, so the equation will take this form. And we know that for this equation, the solution would be of this form, e to the lambda t. If you substitute this assumed solution into the equation, you will get what we call this equation, because e to the lambda t is not 0, so this coefficient has to be 0. So we get what we call characteristic equation. Roots of this characteristic equation will give us the response or the solution to this system. What are these roots? These roots obviously are two complex roots equal in magnitude, opposite in sign. So this would be the two solutions. So the general solution of this equation comprised of a linear combination of these two, where C1 and C2 are some arbitrary coefficient, and therefore the solution will take place as this would be C1 times U1, which is e to the I square root of k over mt, plus C2 times e to the minus I k over mt. However, you remember from Euler complex algebra that we discussed last time, or the first class, e to the I alpha is cosine alpha plus I sine alpha. So if you substitute that into this equation, you get C1 times cosine of k over mt plus I sine k over mt plus C2 times cosine minus I. You can further simplify this by factor out the common coefficients. You will get the equation for the response to be of this form, where C1 plus C2 and I times C1 minus C2, they're basically two constant, regardless of whether they're real or complex, doesn't matter. So therefore, the solution will end up being like this: A cosine of k over mt plus b sine k over mt. So you can see the solution is the sum of two sinusoidal functions, or in other words, is the sinusoidal function itself, okay? Now, I can actually rewrite this in a way that you can see that it is actually one sinusoidal function. How do I do that? If you look at this form, I multiply this equation, the right-hand side, by the square root of a squared plus b squared, and then divide it by the same value. That means I basically multiplied this by 1, right? So that's what you get. You get these two coefficients for cosine and sine term, right? And you see that if I call this quantity alpha, this beta, alpha squared plus beta squared is simply 1. So what do you have here? You have a trig function here, cosine of a function, which let's call that theta, times cosine of omega square root of k over mt plus sine theta times this. And there is a trig, there's a trig identity here. Cosine alpha sine beta, cosine alpha cosine beta, sine alpha sine beta is the sine of alpha plus beta. So this is obviously a constant. So this equation becomes c sine square root of k over mt plus theta. So this is an alternative form to this form. And it shows you very directly that this is the solution is a sinusoidal function. How do you, and what is the sinusoidal function? This is the amplitude of the sinusoidal function, and this is the frequency. Let's focus on this frequency. Let me call this frequency omega sub n is equal to k over m. This frequency of this oscillation is a unique value, and it depends only on the geometric and material property of the system, that is k and m. So the natural or inherent property of a system, and for that reason we call that natural frequency. And natural frequency is one of the key inherent dynamic characteristics of a system. It's almost like a identification card for a dynamic system, because it is a unique value for any system. It depends on stiffness and mass. If you have two structures that have the same natural frequency, their free mechanical vibration would be identical, same frequency, okay? How do you find these constant coefficients now? Well, if you consider this form, okay, form number one, A cosine plus B sine, right? All you need is two initial conditions. So let's say the displacement at time equal to 0 is some value, and velocity at time equal to 0 is given. So if you substitute these into that equation, which is what I have done, at time equal to 0, displacement is equal to u bar naught. This would be sine of omega nt, so it is 0. So you get A equal to u, the initial displacement. And take the derivative of this equation, and substitute again t equal to 0 in that. This is a derivative. I put t equal to 0, so this term cancels out. You get b is equal to u dot naught over omega n, and therefore this is going to be the form of the response in terms of the initial conditions. You can do the same thing for this form if you want to find these two quantities. If you do that, you will see that by substituting at t equal to 0, right? Obviously, u dot would be c sine theta. Taking the derivative, you see that u dot naught would be c omega n cosine theta. And you find, if you solve these two equations for the constants omega, theta and c, this is what you get. So based on these, again, quantities, you can write this equation in terms of the initial conditions. So this is the solution for the free vibration of an undamped system. And the most important conclusion we draw from deriving these equations and writing them is that this represents a sinusoidal function with a frequency that we call that a natural frequency, okay? Now, if you, so here is the other form that I've rewritten here. If you plot this function, is obviously sinusoidal function where theta is the phase angle. So if this is u of t, okay, if this is u of t, at this is the initial displacement, and at this point, what is initial velocity? Is a tangent to this curve, right? It's a derivative of this function, which means tangent to this curve. So this is the initial velocity. This is a sinusoidal function, so the distance between peak to peak or zero crossings is 1 period, which is the inverse of the frequency, okay? So there are other observations we can make. If this is the equation that represents the displacement, if you take the derivative of that, you find the oscillatory motion corresponding to the velocity. So if you take the derivative of this, would be omega n c cosine of omega n plus theta, which is sine of omega n plus t plus theta plus pi over 2. So I'm writing it intentionally in this form. And if you take the second derivative, that means derivative of this, that becomes omega n squared c times sine of this plus pi. What this means is that velocity is 90 degrees out of phase with the displacement, and acceleration is 180 degrees out of phase with the displacement. What does that mean? That means if you look at, for instance, this is the displacement function that you have plotted, okay? So this is the displacement. If this is the zero crossing, at that point, the velocity would be maximum. And when displacement is maximum, velocity obviously goes to zero. So in other words, velocity goes to zero 90 degrees after the displacement has reached zero. Or when this goes to zero, right? Velocity reaches its maximum. That means velocity reaches its maximum 90 degrees after, or pi over 2, after displacement has reached its maximum. That's the meaning of those relationships, okay? So what we have done, we have demonstrated for the free vibration of an undamped system, which is, this is the equation of motion, the response can be derived and written in two distinct forms that you can find these obviously constants, constant coefficient by using the initial conditions. So as I said, this is the first building block for studying mechanical vibration, and it is very important. I want to now show you make a few observations about this simple harmonic motion. Observation number one is, obviously, since this is a sinusoidal function, okay, it repeats itself, right, at every period. In other words, if you consider this is at t equal to t1, and you want to go to a point t2, which is t1 plus 1 period, or 2 pi over omega n, the value of the function would be the same. Or for instance, when it's maximum at a point at the time, which is 1 period after this function reaches its maximum. That's the property of sinusoidal, obviously, function, where Tn is a natural period, as I said. Observation number two, which I mentioned briefly, and it is important, is that the frequency of this oscillatory motion is called the natural frequency because it's an inherent characteristic of the system. The unit for that is radius per second. But also, if you divide this by 2 pi, you come up with a different unit named after the German physicist Hertz, which is very common in dealing with frequencies, okay? Now, the third observation is very interesting. Let me show you. Omega n is the square root of k over m. But what is m? M is the weight over the gravitational acceleration. So if I substitute for that here, omega n becomes square root of k over w times g, right? Or if in terms of hertz, you can convert that to hertz, is 1 over 2 pi this. G in the British unit is about 32.2 times 12, inch per second, okay? So what is W over K though? We have K over W, but what is W over K? W over K means the static displacement of the system under its own weight. For instance, if you have a spring, you attach a mass that has a weight of W to it, right? This is a static problem. How much this mass is going to displace? Force is equal to stiffness times displacement. What is the force here? Is weight equal to K times the static displacement. So you find the static displacement. So this is the static displacement under the weight of the system. So what's the big deal about this? The big deal is this, that you can write the equation for the frequency in terms of this static displacement under the weight of the system. And if you rearrange this, becomes like this, substitute for G the value of 32.2 times 12, take the square root of that, divided by 2 pi. This value, you see that is going to be almost 3.14, which is almost the same as pi. So we can write the natural frequency in terms of the static displacement under the weight of the system as pi over the square root of delta st. What does that mean? That means if you can measure the displacement of the system that it experiences under its own weight, you can estimate the natural frequency of a system. This always reminds me of an interesting problem that I ran into a long time ago, probably close to 30 years ago. There was an offshore platform company. They were designing an offshore platform in a sea, and they were concerned if this is going to survive in that environment, given that the frequency of the ocean wave or sea wave was given. They wanted to make sure they don't encounter the resonance, meaning that that frequency equates the natural frequency of the system. So they wanted to estimate the natural frequency of the platform that they had designed to make sure it is safe. These guys approached a colleague, and that colleague had told them he's going to charge them a big chunk of money, about $15,000, to do some finite element analysis, something sophisticated analysis, to give them an estimate for the natural frequency of this platform. So it happened that they approached me and they said, how much do you charge us? I looked at the problem and paused a bit. And I said, well, I can do this in a few hours or less than a few hours and wouldn't charge you much, just a few $100. They said, how? This is what I did. I told them, do you have any estimate for the weight of this platform? Which obviously they did because they had designed this, right? And do you know what these supported structures are made of? A bunch of, I don't know, steel columns, whatnot. Can you give me an estimate for the stiffness, the total stiffness of this base? They could do that. It's a simple problem. Even if they did, then I could sort of do that assessment. So what do you have then? What was the problem that they have? You have a mass or a weight sitting on a column, which has some stiffness. You have E, I, whatever, length of this, so you can find the stiffness of this. So once you have the stiffness of the column, you have this mass. The problem is simple. It's like that you have a beam under the action of this load at the end that, if you can, its displacement at this point is what? It's WL cubed over 3I from strength of material. So if you have the static displacement under this weight, right? So just simply use Fn pi over the square root of delta over St, and you can find the natural frequency in hertz. As simple as that. Very powerful tool when you want to quickly estimate the natural frequency of a vibratory system. So with that said, we have basically covered everything we wanted to know with respect to the solution of a free, undamped, single degree of freedom system. And that gives us now an understanding of what is the natural frequency. And not only that, as I will show you next time, we can build upon this simple form and do some very interesting problems as far as how to model a complex structure by a single, representing it with a single degree of freedom system. But on a sidetrack, I just wanted to also go over something important, which actually is a question that always comes up. And that is, okay, wait a minute. You're telling me that you have a free vibration, you have a mass, right? And the system is vibrating. And in the equation of motion, right, gravitational force, which is present, does not show up in the equation of motion. Why is that? The reason for that is that if you measure the dynamic displacement from the point of static equilibrium, that is, this weight has already done its job, so now the system is resting. If you measure the displacement from this position, the gravitational force, although is there, does not come into the picture. Let me show you why, okay? Let's say you have a spring, then you put a mass over the top of this. Due to the weight, obviously this is going to experience a static deformation. I call that U sub S. That stands for the static displacement of this spring under the weight of this mass, okay? Now, what I'm saying that if you now measure the dynamic response from this point of reference, equation of motion would be independent of this mg force that is present. How? Let's first measure the dynamic response from here. That is the position where spring has not been subjected to this mass or is in its unstretched, undisturbed position. So if I measure from here, basically what do I have in terms of the motion of this mass? What I have is the free body diagram will be this, or the dynamic free body diagram would be this. You have the forcing due to force of the spring, which has been stretched this much, U prime, the gravitational force, the applied load on the mass, and the inertial force, which I put in the reverse direction. I call that the lumbar force, right? Okay, so in this, with regard to U prime, right, the equation of motion from this free body diagram can be simply written. Mu dot double dot prime plus Ku prime is equal to Ft minus Mg. Remember, U prime is U minus U sub S, okay? So I'm going to substitute for that in here. And remember that U sub S is what? U sub S is the static displacement of this. So it's nothing but the weight over the stiffness of that spring, okay? Now, which is easy to find, right? So if I substitute for U prime in here, okay, given that U sub S is this, okay, U sub S is U minus U prime, right? So I substitute for U prime in this equation, I get what? M times U prime dot, which is M, you're substituting for that, which is U minus mg over k. If you take the second derivative of this is 0 because this is a constant. So you have just U double dot plus k times U prime, which is U minus U sub S, which is mg over k, okay, is equal to Ft minus mg. So you can simply see that this times that is negative mg. So this term and this term cancel out. So what do you get? You get mu double dot plus ku is equal to f of t. That is, if you measure the displacement from the point where the system has already experienced is a static displacement, the equation of motion is independent of the gravitational force. Now, as I asked you in class, now what I want you to do is the following. Demonstrate regardless of basically inclination of the surface where the single degree of freedom system is sitting on. Let's say you have an inclined surface making an angle of theta with the horizon. I want you to prove to say that, demonstrate that if you measure the dynamic displacement from the position where this system has already experienced its static deformation, the equation of motion is independent of this gravitational force. And as I said, for this problem, which I consider as a bonus problem, I'll give you 5 points towards your first set of homework. I add that for any of you who do that, I will add 5 points to your first set of homework. With that said, I'm going to stop here, and hopefully this good, quick overview was a good substitute for covering the actual lecture that I missed to record this morning. Thank you.